I know you got that right, but I think others had some problems. And then I want to just, this is only going to take a second. I just want to make sure you see it. Okay? And before I even do that, does anybody have any other questions or comments? Anything for the good of the group? I know he's William. Jake?
Jake.
And Jack.
Okay.
Han, is that your last name? And I'm trying to learn a few names. With all these masks and everything, honest to gosh, especially Zoom sessions when most of the kids don't turn their cameras on, it's almost impossible. What's in the far back in the corner? What's your name?
Nathaniel.
Say it again?
Nathaniel.
Nathaniel. I think I can handle that. Some of you have had me, and she won't be here today. All right, so no questions? Here's what I want to go over. Now, if you just listen to me, you don't have to write anything. I think I'll make it clear. When we have the TE mode, this is for TE, and we have an interface, this would be region 2, this would be region 1. Now, I'm trying to make this as simple as possible. Because some of you, I think, may have, I can't prove this, but may have looked at references in physics books or Chegg, you've gone there or something like this, and you're going to get really wrong answers. I'm just trying to encourage you to be aware of the fact, even if you ask somebody that supposedly knows, they're probably giving you misinformation. Now, the angle of incidence we talk about always is with respect to the normal of the tube medium. The transmitted angle, that's the angle of incidence, is here. The relationship between the incident and transmitted angle does not mean, has nothing to do with whether it's TE or TM, okay? So this is true for anything. And the relationship is what? In general, we have beta in region 1 times the sine of theta incident equals beta in region 2 times the sine of theta transient. Can anybody tell me the name of that law?
Snell's.
Snell's law. This one you have to know by heart. You don't have to know it for this quiz, but you have to know it by heart. All right, beta in general is omega square root of mu epsilon. That's general. And because square root of mu naught epsilon naught is 1 over c, we can write this as omega over c times the square root of mu relative epsilon relative. And furthermore, if mu relative is 1, it's just going to be equal to omega over c times square root of epsilon relative. Now, what I like to do is just call this beta 0, which is free space, times square root of epsilon relative, mu relative in the region. And here, beta 0 is just omega over c. Good with that? This always works. So if we're looking for the transmitted angle, we have the incident angle, because beta here and here will both have omega over c, and in this case, beta naught, we only care about this. So this is really, if I look at this, if I take beta 1 over beta 2 times the sine of theta incident, I get the sine of theta transmitted. And furthermore, I can say the transmitted angle here will be equal to the inverse sine, or just a sine, of beta 1 over beta 2 times sine theta incident, and we can say theta transmitted if mu relative equals 1 is just equal to the inverse sine. And now it's going to be equal to the square root of epsilon relative 1 over epsilon relative 2 times the sine of the incident angle. That's always going to be the case, all right, if it's losses, all right? and we're only going to deal with lossless cases. Now, you don't have to memorize critical angle. How would you get critical angle for this? Well, in critical angle assumes epsilon relative to, right? Remember, you're going from a less dense to a more dense meteor, right? To do it. And you would actually use this equation and just modify it as need be to get that. I'm trying to be, yes, sir.
Just a quick question, is A sine just arc sine?
Yeah, if you'd like, I'll do it this way. I'm not sure what your calculators have. It's an inverse sign. The opposite of, it's the inverse sign. That's all it is. But you can use that to get the critical angle, right? Because if this is more, or this is less dense, that's more dense, right? Then this goes to 90 degrees. And you find the critical angle in media 2. You all with me? And vice versa. I'm just trying to be clear about this. All right, now, that's always, whether it's TE or TM, it doesn't matter. For TE, remember for TE mode, we have an electric field out of the board, right? It's coming out, right, for TE. Here, we get a transmission and a reflection coefficient, right? Where reflection coefficient is going to, actually transmission is 1 plus reflection. Might as well do it this way. And this reflection coefficient will always have N2, N1, right? Then N2, and these are the intrinsic impedances. Here, it's going to be what? Cosine of theta incident, right? Minus cosine of theta transmitted. This is cosine of theta incident. This is in your book. You don't have to write this down, but you're free to. Cosine theta transmitted, right? Now, hear me on this. We can get, if we have an electric field like coming in that's TE, and you want the angle it leaves at, that's it, right? That's a transmitted angle, correct? Those are no problem. Now, when I come here, if I want the transmitted E field, I take the incident E field, this is the magnitude, times the transmission coefficient right here. And if I want the magnitude of the reflected E field, I take the incident E field times the magnitude of the reflection coefficient. And that's it, right? I know I've said this before, I'm just making it absolutely sure because there's something that's not consistent. You're going to see this when I do the parallel polarization. And therefore, if the incident E field was some E naught incident, right here, e to the minus j beta in region 1, and this is going to be times the sine, right, of theta incident a x plus cosine of theta incident a z. I'm sorry, not a z, x, not f. This would be in the AY direction. What I'm trying to say is the electric field here, that would be, if that's the incident field, I just have a scalar value here. This is the exponential variation. And I might as well, I'll leave it as that. When I take a look at the reflected field, it is just the reflection coefficient for the TE or perpendicular mode. You can use this symbol for TE, or you can use just capital T, capital E, doesn't matter. That times the incident value, right? Then it's going to be e to the minus j beta 1. It'll still be sine of theta reflected, which is theta incident, x, but it'll be minus cosine of theta reflected, z, ay. Are you with me on this? The only thing I've done here is reverse the direction on the actual z component, because when it hits, it bounces back in negative z direction. Clear, class? And I'll do it right here. When I look at the transmitted field, it's going to be E naught incident, right, times the transmission coefficient, that's the TE transmission coefficient, times EXP minus J. This would be beta 2 here, and now there's the sine beta transmitted times X plus cosine of beta transmitted times Z, and this is still AY. You can get the H field components according to the direction of propagation crossed in the E divided by 8 in the regions. I'm not going to bother doing it. The E field's critical, all right? Here's where the problem is. So all that's for TE. When we have TM mode, often called just parallel, now this is region 1 and this is region 2. This is the incident angle. This is the transmitted angle. Here, the electric field incident has components that are both X. Oh, I didn't put this in here. This is Z, and this is the X-axis. So this is Z, and this is the X-axis. It has components. This is the direction of the E field for TM mode. In the plane of the board, it has both X and Z components, right? Here's where the problem exists. Some people just take I'm going to put it down there, the transmission coefficient, and they multiply it by this value. You don't do that. Everybody understand it? I'm going to show you how to do it. So just make a note of this. This is where the mistake is. When I do this problem, I want to find the transmitted field, right? And I want to find the reflected field. But the thing that's continuous is going to be the actual magnetic field. H tan 1 is equal to H tan 2. And I mean, it's really H incident plus H reflected is equal to H transmitted. When you go through the math on that, what you end up with this. You get a reflection coefficient equal to, I like doing it this way always. I put beta 2. I know this is going to be a cosine minus beta 1. I know this is a cosine. This is 82, I know it's a cosine, and it's a plus, and I know it's eta 1. I know it's a cosine. And the only thing I have to do is get the angles right. Well, last time, this was actually what? Incident, right? For T, it becomes transient. And this becomes incident. I know that's the reflection coefficient, correct, everyone? The transmission coefficient is going to be 2. Again, I like to do it this way. Put 2, eta 2 here. I know I have eta 2 plus eta 1 here. This will be cosine of theta incident, right? I mean, if you don't remember it, it's not a problem. I'll give you these. I don't expect you to. Are you with me on this? And then this becomes cosine of theta transmitted, right? And this is cosine of theta incident. Now check that with me. Y'all remember, remember the subtleties, right? How many remember that? All right, if you don't worry about it, but you should at least be familiar enough. I mean, this should ring bells. You should remember. Now, what does that transmission coefficient actually mean? And this is important. Because this is the transmission coefficient defined in the book. That transmission coefficient is equal to the magnitude of E transmitted over the magnitude of E incident. And you might as well call it E naught transmitted, E naught incident. Are you with me? It's the magnitude. It's not just the EX multiplied by the transmission coefficient or just the EY. It's the magnitude of the two. Got me on this one? It's real important because you'll make a mistake if you do it that way. If you just take transmission coefficient times EZ to get the transmitted EZ, So we get this, and this is true. And now When we want the transmitted E field, I'm going to stop right here. The actual transmitted E field for this would be the TM mode or parallel mode, is going to be equal to the transmitted E field's magnitude. And then you're going to have, for this one, you're going to have a cosine of theta transmitted, AX here. And if you look at this, then you have minus a sine of theta transmitted right here, AY. And then you'll have the exponential term. This is in his book. It wasn't really brought out. So this is going to be minus J beta 2 times those sine and cosine terms. Okay, class? Now hear me. Here's the problem lines right there. All right, what people generally do is they just take, I didn't break out the E field in terms of X, Y component. They'll have the E incident X times transmission coefficient, and they're going to put it down as the X component, and they won't take and factor out E naught T. Now, I know that you did this right, but I'm sure a lot more people did it wrong because of that. I'm just warning you on this, okay? There was an example I gave you. That's the only thing I'm going to do in class. I'll have the solutions for this up, and I'll get your stuff back on Monday. But I wanted to clear this up because it was kind of, I could understand why people did it. How many made that mistake, by the way? Nobody? Well,
Yeah, I don't.
There's maybe you're not aware of it, but there's plenty that made it, I believe. Okay, that's that. Now, and one last thing. How do you get the magnitude of the transmitted field? How about I get the magnitude of the incident field? Let's try that approach. This I have, don't I? What do? I take the EX and EY component, or EX and EZ components, square both of them, take the square root for the incident. Follow me on this, guys? That's the magnitude. You get the, once you get the angle of transmission, then you have the cosine and you have the sine. So you have the weights in front of AX, in front of AX and AZ, correct, class? For E. It's important you do this. All right. So today, I want to just summarize waveguides, rectangular waveguides, then move on to really fiber optics and optical waveguides that are planar. Now, fiber optics is probably the single most important thing, but to really do fiber optics correctly, we have to do circular waveguides. We can get away without doing them, but I'll explain this. Actually, you don't have to do it, but it's helpful. So now today, I want to finish up with a waveguide. This is the summary. Are the things I'm posting helpful in OneNote? I got the field quantities all posted for you. Got everything that I, as a student, would want in front of my face. And you can print them out, just post them in your, put them on the walls if you need to access them. So when what you have a summary is really, a waveguide replaces a transmission. That's what it does, right? We want the waveguides to work at only one frequency if we're, for a rectangular guide, if we're trying to do things right. So generally you want the frequency of operation between the cutoff frequency for the 1.0 and the cutoff frequency for the 2.0 mode. That's where you want to, this is ideal, by the way. Okay. You don't have, yeah.
So that little FC number line that you have with like 1, 2, 3, 4, and then it has all the TE operations for each cutoff frequency. You know what I'm talking about?
You're talking about find the cutoff frequencies for each mode in the waveguide. Right? The
Right.
MN values?
Right, so if you have all these like TE30, TE21, all that, if we never want to use that, then are we never going to use those higher if we're only trying
Here's
to...
how come you have to know. Because some of the advanced stuff that you'll get into, you have to be aware of how to calculate that mode. because you can send two modes down a waveguide, but here's the thing, when you do that, you don't have both going to the same mode. You have what's called a splitter, and it will take the 3.0 mode and route it one way, and then it'll take the 1.0 mode and route it that way. That way you get away with one waveguide. Now, is that ideal? No, because there's always bleed over. You can never get all the 3.0 mode going one way. Some of that bleeds that way, and it can cause problems. They do that when they can't retro, at least one of the reasons on an aircraft carrier. I was on the Eisenhower, right, as a consultant on electromagnetic warfare, electronic warfare. They have waveguides all over the ship. They got radars all over it, all right? Putting one more waveguide in there is an absolute pain. So what they can do, and I don't know that they do, they can route two different signals on the same waveguide, knowing that they have to go ahead and separate. That's usually for things that aren't mission critical, like a communication link or maybe a long-range navigational radar. But I'm going to just leave it at that. Those modes are important to know, just to understand what the frequencies are. This is the typical 99.99% of everything I've ever done in my life operates in this frequency for a rectangular guide. Now, cylindrical guides are a little different, and I don't have a lot of experience with them. Now, anyway, for that, that's ideal. The next thing is to figure out if a waveguide, if it has a cross section A, height B, and its conducting sides, and this is going to be length L. Next thing you have to do is find out the cutoff frequencies. I will give you this, by the way. Cutoff frequencies for the M in mode, and that's really equal to 1 over 2 square root of mu epsilon, square root of M over A plus N over B. M and N are the mode numbers. We've been through this, right? You want to find the lowest value. What is the lowest cutoff frequency? It's called the fundamental mode. Anybody?
T10.
Yeah, the 1-0, right? The 1-0 mode. And that's, since it's 1 and 0, the square root of 1 over A squared is 1 over A. It's really 1 over 2 square root of mu epsilon divided by A. And if it's air-filled, it's just C over 2A. And that's where half wavelength fits right there, the frequency, the cutoff frequency. Remember that, everyone? So that's what you do. This is really, that's the cutoff. The cutoff for the 2.0 mode is just equal to 2 cutoff of the 1.0 mode. That's it. I'll leave it like that, okay? You all with me on this? Now after that, I would give you this equation. You have, well, actually, I don't give you this. You have to determine what the characteristic impedance of the guide is in the respective mode. If it's a TM mode, this is the characteristic impedance. So I'm going to call it Z0TM. That's the intrinsic impedance of the region. And here, this is equal to square root of mu over epsilon, or really 120 pi square root of mu relative over epsilon relative, and that's in the dielectric right here. I think you have this, this is something. So this typically is 120 pi, but if it's Tm, it's multiplied by K. And I like K because I'm going to use it over and over again, so I only write it once. K is equal to 1 minus the quantity Fc, whatever mode you're in, over F squared. And you'll notice when Fc is equal to F, then it's 0. And when it's 0, that means the characteristic impedance is 0 for Tm. For TE mode, it's equal to this divided by K. So for the TE mode, the impedance is going to infinity at cutoff, right? And we're going to add one other thing here. If I looked at a plot the impedance of ZTE right here versus F, what'll happen is, if this is the unguided impedance, it'll come in from infinity and asymptotically approach that. Then if I take a look at the characteristic impedance for the TM, it'll do this. Asymptotically, they're overlapping. Follow me? Important. Okay. After that, next thing I'm going to say, and I set this problem up last time, remember you can treat a waveguide just like you would a transmission line with these slight modifications. First, the characteristic impedance is different. Then, the input impedance will be equal to Z naught of whatever mode it's in. So this is a modal value here, right? It depends on frequency because it depends on K. It's either this or this, okay? Typically, it's TE1 mode. Then it's going to be times Z load, whatever the load is. I will give you this equation. I cannot overstate the fact I don't expect you to memorize it. Plus Z naught, I didn't used to, but I'm doing it now. And this is important. Beta in the guide here, right? Remember what it's equal to?
Beta U times K.
Right. It's equal to beta unguided times K, right? It goes to 0, right, at cutoff, right? Now, also the wavelength in the guide is equal to 2 pi over beta in the guide, right? And if you look at that, y'all follow me on this? Because wavelength times beta is 2 pi. That's how you get wavelength. Now you can see, well, if the guide's going to 0, the wavelength goes to infinity at cutoff. That's another important thing to note, all right? The phase velocity is equal to really the velocity increaser in an unbounded media. And I'm just going to call it 1 over the square root of mu epsilon, because that is the velocity of any kind of electromagnetic phenomena, propagating electromagnetic phenomena in an unbounded region. All right, just the regions filled with epsilon relative mu. It's that, and then the phase velocity is divided by k. The group velocity, or the velocity of energy, is going to be 1 over the square root of mu epsilon here, and it's times k. Now that's important because, yeah.
In the example in the last homework, that phase velocity is greater than the speed of light.
Absolute. Phase velocity goes to infinity at cutoff. And I'll try to make it clear to you and everybody else. I really do try to tell you about phase. Assume that this line right here is the shoreline. I love this example. All right? If I have a wave, crest of an ocean wave moving this way, the intersection point of that crest with this line, the shoreline, is moving at the same velocity as the crest, right? Now move it down like this, right? The crest is moving like this. This is moving much faster, right? What happens when it comes in like this? It's tending to infinity, isn't it? That's what the wave just bounces up and down. If you looked at the imaginary point where the peak of the electric field's magnitude, if it's a plane like that, bouncing here, it's moving about infinite, right? Much, much faster. Thing about phase velocity, it's not the velocity of anything, any type of energy right now. The only thing it is a definition of where 2 points intersect, and that can be much, much faster than the speed of light. Phase itself does not have any kind of energy associated with it. It's a group, okay? That's so important because you're going to see all sorts of stuff. let me tell you this. You're engineers, right? You had physics. One thing you know is you get nothing free. You can't get something for nothing. Whenever they talk about these perpetual motion machines and this things that are creating energy out of nothing, they're all over the internet. Trust me, there's all these loose cannons that see a little bit of truth, and they make these huge jumps. One of the things they use is phase velocity. They're getting faster than the speed of light, so the energy is going to astronomical for anything moving that fast. And it would seem they have a legitimate argument. You know, remember that. You're smart. Nothing of real meaning, no energy or mass moves faster than the speed of light. And you can read about all sorts of stuff later, because this is stuff that physicists love, this stuff, astrophysicists. Let me just finish my thing. They're going to get something with, if you know what the event horizon is on a black hole, they're going to show something kind of bizarre. There's a mathematical oddity where they're getting things moving faster than the speed of light. Actually, that stuff is things that are disproved over time. It doesn't work. But you can have phase moving faster, because that's an abstract point. Go ahead. I mean, you know what a black hole is? I use this term as if it's just what? It's mass where you lose any form of an atom. Neutrons, protons, electrons, anything else in there is crushed down and it becomes something where, without getting into I'm not one of these nuclear physicists. Basically, you get things that are poorly understood. A black hole keeps on crashing in until something happens, and that something that happens is called a supernova, I think, when it explodes. And why it explodes and how it explodes, they're scratching their heads on that one. But it's interesting. You're all scientists and engineers, you're very bright. These things at least should pique your curiosity. Okay. That's about all I wanted to say about waveguides, except one thing that we do, just like with transmission lines, when I put a load there, you have to know the length of the waveguide. You have to know the reflection coefficient of the load, right? You all with me on that? And you have to know, you basically have to know from the equations I gave you how to get voltage at the load, right? How to get voltage just on the inside of a conductor if there is a source resistance. Does everybody remember me going through that? I really made it a point. Okay. I'm going to move on, actually. I'm start giving you your quiz now, but now you have physics here. Do you remember that they did a lot with optics and index of reflection, stuff like that? Did that?
Mm-hmm.
I'm going to just springboard into fiber optics and really slab waveguides by mentioning one thing. And I know you're going to write it down, but you don't have to. I know you're anxious for your quiz. But here's what it comes down to. When I have a fiber optic system, I basically have a core, like such. And this is called, there's an index of refraction called a fiber index of refraction. It's equal to the square root of epsilon relative of the fiber core. And it's surrounded by a cladding like this. Fiber optic cables are round. A lot of reasons for that. Now here's what really happens with fiber optics. You look, and this is going to, actually let's call this, I'm sorry, in the book he calls it core. I see this, and this is called actually the cladding. So I'll just call this CL here. It's equal to the square root of epsilon relative to cladding. Well, here's what really happens and why it's important. This is the angle that means so much. Right here. It's the critical angle between these two things because we want all the energy to bounce off here and continue bouncing. So we have to have the light that's going to propagate down coming in at least this angle to the normal incidence or greater than that. Do y'all follow me? I'll spend time Monday to really make this clear. Anything less than that, some of it will propagate, and then as it ricochets down the waveguide, it'll be gone in no time. Does that make sense to everybody? So you want to make sure you're at the critical angle or better. What that translates into is you come down here. If this is the critical angle, I come to this interface right here between this region and air. If that's the critical angle, this is going to be 90 degrees minus the critical angle. And that means this is how the wave would travel. Here's the interface right here. Let me just do it this way. You take a cross cut of this, the waveguide. We've got critical angle here. That's supposed to. Then here, this angle would be 90 degrees minus the critical angle. And this angle we call the angle of incidence. And what we do is we figure out the angle of incidence you have to be coming in at this angle or less for propagation to occur. And I'll go through that Monday, but I wanted to give you a heads up. What we do is always look at the critical angle for these things. Now, what I'd like you to do is fill up this row, leave that blank, fill up this row, and leave that blank. You don't have too bad of time. And just move over to it. I'm trying to get everybody's space. And I'm going to give this. And would you do me a favor? Remember, no